Hello, welcome you all for video lecture for thermodynamics, session number 4. In this video, I am going to derive equation of state of a gas in adiabatic process. I am Dr. Srinivasa, working as an assistant professor of physics in IDSG Government College, Chikmagalur. So in this video, I am going to explain and derive equation of state of a gas in adiabatic process, the relation between pressure, volume and temperature in a adiabatic process, and also I will going to derive work done during isothermal and adiabatic process. So first, I am going to derive an equation of state of a gas in adiabatic process. So dear students, you already know that what is an adiabatic process. Adiabatic process is one in which pressure, volume and temperature of the system changes, but heat neither enter the system nor leave the system. That is dq is equal to 0. So what is the equation of a state of a gas in adiabatic process? The equation of a state of a gas in adiabatic process gives the state of adiabatic process at any instant of time. So to derive the equation of a state of a gas in adiabatic process, let us consider a unit mass of an ideal gas contained in a perfectly non-conducting cylinder fitted with a non-conducting piston. So we have to consider a cylinder of non-conducting walls fitted with a piston of a non-conducting walls also, because in the adiabatic process heat should not enter or leave the system. Then only the process is called adiabatic process. That is why we are taken the ideal gas of unit mass which is enclosed in a cylinder containing a non-conducting walls and also fitted with a frictionless piston of non-conducting walls. Let P is the pressure, V is the volume of the gas and T is the temperature of the gas inside the cylinder respectively. Suppose a gas is compressed adiabatically. So by moving the piston from this position to this position, we can compress an ideal gas using the piston, so that the piston moves inwards through a distance dx. Let dx is the distance moved by the piston from this position to this position. If A is the area of cross section of the piston and F is the force applied, then you know that force applied is equal to pressure into area, because you know that pressure is equal to force by area. Therefore, force is equal to pressure into area. And also you know that work done by the piston is equal to force into displacement. And also substitute for the force from this equation. So force is equal to pressure into area and the displacement is dx here. But A into dx gives the change in volume of the gas when the piston is moved from this position to this position. So A into dx gives the dV. Therefore, work done by the piston is given by dW is equal to P pressure into A dx is dV. Here dV is equal to A into dx gives the change in volume. The heat generated due to the compression causes a rise of temperature dt and is given by Cv dt, where Cv is the most specific heat at constant volume. And also you know that, so in your early classes, the definition of specific heat gas at constant volume is given by dQ is equal to CV dt. That is the heat generated due to the compression. When we compress this gas, its volume decreases. As volume decreases, pressure increases. As pressure increases, temperature increases. So when this piston is moved through a distance dx, the rise in temperature is given by dt. So and also it is given by CV dt, where CV is the most specific heat at constant volume. And also you know that according to the first law of thermodynamics, dq is equal to du plus dw, that is amount of heat supplied to the system is equal to change in internal energy plus work done by the system or on the system. And also you know that dw is equal to pdv in the previous expression. So dq is equal to du plus pdv. For an adiabatic change, dq is equal to 0 because heat neither enters the system nor leaves the system. So dq is equal to 0. Substitute 0 for dq, will get du plus pdv is equal to 0. So finally we get du plus pdv is equal to 0. Call this as equation number 1. And also we know that specific heat at constant volume CV is equal to du by dt. Hence du is equal to CV dt. So change in internal energy is equal to specific heat at constant volume into rise in temperature. So here CV is equal to du by dt or du is equal to CV dt. Substitute the value of du in the equation 1, we get, so du plus bdv is equal to 0. For du, substitute CV dt. Therefore, equation 1 becomes CV dt plus pdv is equal to 0. Call this as equation number 2. The equation of state for 1 mole of perfect gas is also given by PV is equal to RT. For n moles, PV is equal to nRT. For 1 mole of a gas, PV is equal to RT. Differentiate this equation, we get. So here R is a constant, but in the adiabatic process, all the thermodynamic coordinates such as pressure, volume and temperature changes. Therefore, on differentiating this equation, we get P into dV plus V into dP is equal to R into dt. R is a constant, so that is why only R dt. So P into dV plus V into dP is equal to R into dt. Then equate for dt. So dt is equal to pdv plus vdp over R. Call this as equation number 3. So finally we get equation for change in temperature or rise in temperature, dt is equal to pdv plus vdp by R. Substituting the value of dt in equation 2, we get the equation number 2 is cv dt plus pdv is equal to 0. But dt is equal to pdv plus vdp by R. Then cv into pdv plus vdp by R plus pdv is equal to 0. So take LCM, we get cv into pdv plus cv into vdp plus R into pdv is equal to 0. So on simplification, this equation becomes cv into pdv plus cv into vdp plus R into pdv is equal to 0. Here take pdv as common from these two, cv into pdv. Here R into pdv is there. Take pdv as common, we get cv plus R into pdv plus cv into vdp is equal to 0. Call this as equation number 4. And also we know that from the Mayer's equation, specific heat at constant pressure Cp is equal to Cv plus R. So substitute for Cv plus R as Cp in the equation 4, we get Cv plus R is equal to Cp. So Cp into PdV plus Cv into VdP is equal to 0. So from equation 4 and 5, we can write Cp into PdV plus Cv into VdP is equal to 0. Dividing both sides by Cv, Pv, we get, divide this equation by Cv into Pv. So we get, on dividing this, we get Cv, Pv get cancelled. So Cv, V get cancelled. Then we get, so dP by P here, this equation. Cv, V by P. dP by P plus Cp by Cv into dV by dV. I have written this term first. So dP by P plus Cp by Cv into dV by V is equal to 0. And also you know that Cp by Cv is the ratio of specified constant pressure to the specified constant volume, and it is equal to gamma. Therefore, dP by P plus Cp by Cv, substitute gamma. Gamma into dV by V is equal to 0. Next, integrate this equation, we get integration of 1 by P into dP is log P plus gamma into integration of 1 by V, dV gives log V is equal to C. So on integrating this equation, we get log P plus gamma log V is equal to C, or log PV to the power of gamma is equal to C, that is constant. So take this gamma log V can be written as, so log A plus log B is equal to log A by B. Like that, we can also write this as log A plus log B is equal to log AB. Sorry, log P. Log A plus log B is equal to log AB. Log A is P. Log P into gamma log B can be written as V to the power of gamma. So is equal to C. Take exponential on both sides, we get log and exponential get cancelled. We get PV to the power of gamma is equal to E to the power of C, where C is a constant. And PV to the power of gamma is equal to K, where K is another constant. E to the power of constant is another constant K. So if P1, V1 is the pressure and volume at a state 1, and P2, V2 are the pressures and volume at a state 2, then this equation can be written as P1, V1 to the power of gamma is equal to P2, V2 to the power of gamma. So this is the equation of state for an adiabatic process in terms of pressure and volume. This is the equation connecting pressure and volume during an adiabatic process. Then what is the relation between pressure, volume and temperature? We will derive the relation between the temperature and volume first, and then pressure and temperature. So we know that PV is equal to RT is the perfect gas equation. From this equation we can write P is equal to RT by V. And also you know that PV to the power of gamma is equal to constant. We derived in the last slide. So P is equal to RT by V. So PV to the power of gamma is equal to K. Substitute for P from this equation as RT by V. So for P, substitute RT by V into V to the power of gamma is equal to K, where K is a constant, but R is also constant, universal gas constant. So therefore, here R is a constant, so T is there, denominator V is there. So take to the numerator, it becomes V to the power of minus 1. So then this V, volume becomes V to the power of gamma minus 1. So TV to the power of gamma minus 1 is equal to constant. This is the relation between temperature and volume for an adiabatic process. Also we know that from this equation PV is equal to RT. So V is equal to RT by P. And also we know that PV to the power of gamma is equal to constant. Substitute for V here. So, and simplify. P is there for V. RT by P all to the power of gamma. So R to the power of gamma, T to the power of gamma or P to the power of gamma is there, and also P is there. So R to the power of gamma, T to the power of gamma, and so here P is there. Take to the denominator P to the power of minus 1, P to the power of gamma. So P to the power of gamma minus 1 is equal to constant. Or T to the power of gamma over T to the power of gamma minus 1 is equal to constant by R, or R to the power of gamma, since R is a constant. So from this equation we can written as P to the power of gamma minus 1 over T to the power of gamma is equal to constant. Once again, P to the power of gamma minus 1 over T to the power of gamma is equal to constant is the another equation for adiabatic process. Work done during an isothermal process. We will derive the expression for work done during an isothermal process. Dear students, you all know that what is isothermal process. Isothermal process is a thermodynamic process which takes place at constant temperature. The PV diagram of the isothermal process is represented by AB curve, and this is also called isothermal. And also you know that area under the PV diagram or indicator diagram gives the work done. So by calculating area under this isothermal curve, we can calculate or obtain the equation for work done during isothermal process. So area under AB graph, that is PV diagram, gives the work done. So when a gas is allowed to expand isothermally from A to B, work is done by the gas. When the volume changes from V1 to V2, V1 is the initial volume and V2 is the final volume, work done is given by, you already know that, by integrating. So V1 to V2 PdV. So work done, expression for work done is given by, so dW is equal to PdV. The total work done is given by integrating V1 to V2 dW, that is PdV, that is equal to area under AB curve or area of ABCD. By calculating the area of ABCD, we can calculate the area under the graph, PV graph during isothermal process. For 1 gram molecule of the gas, PV is equal to RT, and also P is equal to RT by V. Substitute for P. So work done W is equal to integration of V1 to V2. For P, substitute RT by V into dV, that is equal to RT into ln of, logarithm of 1 by V is, so log V converted into common logarithm by multiplying 2.303. So RT is there, it is a constant because R is a universal gas constant and T is at constant temperature isothermal process takes place. Therefore RT is a constant. The integration of 1 by V dV is log V, lower limit V1, upper limit V2. So on simplification we get and convert that natural logarithm into common logarithm, RT into 2.303 log 10 V2 by V1. Call this as equation 1. Also we know that P1 V1 is equal to P2 V2. So therefore V2 by V1 is equal to P1 by P2. So V2 by V1 is equal to P1 by P2. Substituting for V2 by V1 in this equation, we get work done is equal to RT into 2.3 log base 10. For V2 by V1, we can write P1 by P2. So this is the expression for work done during an isothermal process in terms of the velocity, and this is the equation for work done during isothermal process in terms of pressure and in terms of pressure. Hence, the change in the internal energy of the system is 0 because temperature constant. In the isothermal process, temperature remains constant since internal energy depends upon the temperature. So therefore, change in internal energy is also constant. That internal energy is constant. Therefore, change in internal energy is 0. So the heat absorbed by the system is equal to the work done by it. Next, we will derive work done during an adiabatic process. So, and also you know that adiabatic process. In the adiabatic process, all pressure, temperature, volume changes, but heat neither enters the system nor leaves the system. So the PV diagram during adiabatic process is given by the curve AB. Once again, area under this curve AB gives the work done during the adiabatic process. So work done when the gas expands from V1 to V2 is given by work done is equal to integration of dW, that is V1 to V2, dW is PdV, that is equal to area of ABCD. During adiabatic process, PV to the prop gamma is equal to constant, that is K, or P is equal to K by V to the prop gamma. Substitute for P is equal to K by V to the prop gamma. In this equation, we get work done W is equal to integration V1 to V2, K by V to the prop gamma dV. K is a constant. Integration V1 to V2, V dV is given by. So on integrate V dV, get V to the power of 1 gamma minus 1 minus V to the power of 1 by V, that is K over 1 minus gamma. Here miss is there, V to the power of gamma is there, V to the power of minus gamma is there. It is a missing here. It is not V dV, it is V to the power of gamma dV. So V to the power of minus gamma dV. This is V to the power of minus gamma dV because it is 1 by V to the power of gamma. Take to the numerator, it becomes V to the power of minus gamma into dV. So on integrating V to the power of minus gamma dV, we get V to the power of minus gamma minus of minus plus 1 over 1 minus gamma. So therefore we can write 1 minus gamma, take outside, K over 1 minus gamma or 1 minus V to the power of gamma minus 1 minus of V1 gamma minus 1. Since A and B lie in the same adiabatic, so we can write P1 V1 to the power of gamma is equal to P2 V to the power of gamma is equal to constant K. So work done is equal to 1 by 1 minus gamma. Take K inside the bracket. So K over V to the power of gamma minus 1 minus K over V1 to the power of gamma minus 1. So work done is equal to 1 over 1 minus gamma into. So here PV is equal to constant K. So K can be written as here P2 V2 to the power of gamma over V to the power of gamma minus 1, and also here K can be written as P1 V1 to the power of gamma over V1 to the power of gamma minus 1. On simplification, work done is equal to 1 over 1 minus gamma into P2 V2 minus P1 V1, because here V to the power of gamma minus 1 is there. Take to the numerator, it will becomes V2 to the power of minus gamma plus 1 minus gamma plus gamma get cancelled, then V2 to the power of gamma is there. Sorry, V2 to the power of 1 is there. So here also P1 V1 remains there, and V1 gamma, minus gamma plus gamma cancel, V1 to the power of 1 is there. So that is why we get work done is equal to 1 over 1 minus gamma into P2 V2 minus P1 V1. This is one of the expression for work done during adiabatic process. Similarly, for P1 V1 is equal to RT1 and P2 V2 is equal to RT2. So R is a constant. Therefore, work done is equal to 1 over 1 minus gamma. We can write for P2 V2 RT2 and for P1 V1 RT1, and take R as common. Work done is equal to R over 1 minus gamma into T2 minus T1. Or here 1 minus gamma is there. Replace with the minus sign. We get R over gamma minus 1 into T1 minus T2. So these two are the expression for work done during adiabatic process in different forms. It is in terms of pressure and volume. It is in terms of temperature and also R. So I have used all these books as reference to make this video. Thank you for watching. Thank you once again. So all of you subscribe my channel